The powers that be, I think some of that are sitting in here, I think would be okay if we just move the pillars.
Where you can still see the screen.
All right.
Then after that,
Come
it might
around
be
to the front. Please, come on in. All done.
almost.
Okay. I'm actually going to start. John, come in. Unless you don't want to. It is cozy. I suppose we could open up a door or two and look at the fresh air. You're going to pass. Okay. All right. So let's just start. So first of all, you can color me impressed. I've never drawn this many people to it. But thanks, Bob, for agreeing to do this. So this is very much an ad hoc talk, arranged hastily over the last couple of days. What happened is about 3 weeks ago, a group of about 14 of us took a trip down to Holmdel, where Bob very kindly invited us to show us around there. Also, we've been doing some DSP work across the street, and there's a DSP group down there we spoke to, and we actually spent about 2 hours talking to that DSP group. So when John Kovac takes his experimental astronomy students down, Bob usually gives us...
What's a DSP group?
Digital signal processing. Yeah. So there are people doing research down there that Bob wanted to introduce us to, so that was kind of the impetus. Anyway, Bob usually gives this talk as part of the visit, but because we have this 2-hour meeting, he didn't fit it in, so he offered to do it here, and then on a whim, I thought, well, let's advertise it widely, and Bob went for it, so that was great. So Bob spent over 30 years at Bell Labs, and he joined SAO after retiring in 1994. Which means you've been over 20 years here. So we've been, well, it's a significant amount of time, so we've been very fortunate, I guess. He's done many things over those decades, being the technical lead during the construction of the SMA. That's the sub-millimeter array. In the last couple of years, my group's been lucky to have him contribute to digital signal processing. In particular, he's worked directly on the conversion fidelity of ultra-high-speed analog to digital converters that we're using in new back-end instrumentation that we're developing for the sub-millimeter array that's actually just been activated in the last year. So he's going to tell you about the many things he did at Bell Labs. I won't tell you about those. But something I think that is really notable is, in his history, is a little anecdote that some people here may not have heard of. A couple of years ago, when Hurricane Sandy hit New Jersey, it took out the power at Bob's house and ended up being out for about 2 weeks. I think it was like just a couple of hours or maybe a couple of days, a day later, that Bob's emails started showing up in my inbox again. It somehow got back online. So it turns out he'd wired up his house to his Toyota Prius and was able to get a couple of loads of laundry in, keep the food cool. And so, that's the kind of guy that Bob is. So I'm going to give this talk.
Thanks, Jonathan. We survived 11 days of no power with 8 gallons of gasoline. Because you also couldn't buy gasoline because the gasoline stations didn't have power. So this is a little expanded over what I usually do for AY191. I'm going to try to tell how a small group at Bell Labs dedicated to making a better long-distance telecommunication ended up contributing to radio astronomy in several important ways. So let's see. Skip that for the moment. In the 1920s, Bell Labs was in New York City on West Street. They had a big building, and we're doing a lot of things there. But the people who were interested in telephony and radio telephony found there was a lot of electrical noise in the city. And so they established several field stations in northern New Jersey. And by the early 30s, they had been consolidated in Holmdel. And this is a picture of the group next to the what's lovingly called the turkey shed that they worked in. And there are a few people in here who are important to this story. Art Crawford, Karl Jansky, Marlon Sharpless, forget Bruce's first name, and Al Beck. And these people come up in time. In 1928, Karl Jansky and Art Crawford were hired, and for a while they roomed together. They later got married, had families and so forth. Karl was tasked with understanding the sources of noise on the proposed transatlantic shortwave radio telephone connections. He built this large 95-foot directional Bruce array. I forgot to point out Bruce. And a sensitive radio receiver. And you can see that it's mounted on Model A wheels, and it rotated slowly. And he had a chart recorder, recorded the amount of noise coming in throughout a long period. He discovered thunderstorms, of course, man-made noise, but he found a hiss-like noise which came up about once a day for a while. And of course that was later, after he talked to an astronomer and figured out why it was different 4 minutes every day, he figured out it was coming from the galactic center. And that was the beginning of radio astronomy. And so this appeared on the front page of the New York Times. And you might notice that he says there's no indication of any kind that these galactic radio waves constitute some kind of interstellar signaling. And so no little green men at this point. There was one more report of star static, as they called it, from a multi-element steerable array, probably one of the first phased arrays that was built in the 30s. And they probably observed the Cygnus region in the galaxy. Unfortunately, Karl, even when he was hired at Bell Labs, had a chronic kidney disease, and he died in the late 40s and never really saw radio astronomy become a big thing. But later on in the 30s, the group moved to microwaves and started thinking about microwave relays. During the World War II, they worked on radar, but at the end of the war, they were all prepared to try out a microwave relay system. The first, the so-called TDX system, used this kind of station, and they had this horn, a large horn with a large taper, which of course would have a very large phase error and wouldn't be very effective, but they had an artificial dielectric lens. But one of the early concepts was a horn on the ground looking up to a reflector up in the sky. And I guess I found this one somewhere. No one had ever told me about this. But of course, a large aperture horn with no correction has to be very long so that the taper is slow. And one day Al Beck was thinking about this and decided there must be something better than a plane reflector to put at the top. And so he got out pencil and paper and started remembering calculus of variations. And he decided to solve for what would turn this expanding signal into a plane wave. And in the end, of course, he was chagrined that he'd reinvented the paraboloid. So all future systems use the Horn reflector. This is a diagram of how a Horn reflector, conceptual diagram of a Horn reflector. This is the paraboloid, the reflecting surface there is just a section of that paraboloid 90 degrees away from the axis. And these things were used in many microwave systems. I think when I was a boy in 1950, we got television in Houston, and it came over just such a system. Well, skipping ahead a little bit, John Pierce was a polymath at Bell Labs. He had written the book on electron beam guns. He contributed to communication theory. He outlined the usefulness of PCM with Barney Oliver and Claude Shannon. He supervised the transistor team and coined the name transistor. He started what was probably the first computer music group, if not it was very close to the first. And he also wrote science fiction under the pseudonym J.J. Cutling. And I think it was this last activity that resulted in 1955 in a paper he published in the magazine or journal Jet Propulsion titled Orbital Radio Relays. He was apparently unaware of Arthur Clarke's extraterrestrial relays, which had been published in Wireless World in 1945. Anyway, in 1957, when Sputnik went up, John was all prepared, thinking about what he wanted to do, and especially in 1958, NASA proposed putting up the 100-foot diameter Echo balloon made of half-mil aluminized mylar. They wanted to measure the forces in orbit by having a very light, very large thing. Then any small force would change its orbit. But John realized that this could be a test satellite and that you could worry about earth stations, how you point, track, and so forth, and learn a lot before you actually had a usable satellite. So Bell Labs proposed using Echo as the first communication satellite. The return signal would be weak. You've got this spherical satellite, you have a plane hitting it, plane wave hitting it, and it's scattered. The plane wave is scattered in all directions. It's not redirected back to the Earth. So they decided to use some things invented at Bell Labs. They had made a traveling wave Ruby Maser, which was the lowest noise microwave amplifier you could get at the time. That was part of the Cold War effort. And the Horn reflector, of course, had been designed before then. And Art Crawford was given the responsibility of building the 20-foot Horn reflector. As you can see, with the receiver back in here, the horn shields the receiver very well from the ground. So measurements had been made that showed that the back response of such an antenna was extremely small, but much more than 30 dB below isotropic. So we could expect to have a very small ground pickup. So Echo was launched and used as a microwave relay. In 1960, Eisenhower's voice was transmitted by JPL, received at Crawford Hill, sent out over the radio, over the lines to the radio, and the world's first communication satellite operated. Meanwhile, Bell Labs was working on Telstar, the first active communication satellite. It was launched in 1962, and the 20-foot Horn reflector had a backup role there. As it turned out, the French actually got their station going, so there was nothing much to do at Crawford Hill other than monitor the beacon. Well, in 1957, I went to Caltech for a PhD in physics, and Sputnik was launched that October. I realized this was an important thing, but I don't think I realized how important it was going to be for me, the results from Sputnik. I, for other reasons, joined a new radio astronomy group at Caltech, which had just done the major construction for the first Owens Valley interferometer, 2 90-foot antennas. During that period, my one cosmology course was taught by Sir Fred Hoyle, and philosophically, I really liked the steady state theory that he had been part of. Well, he was really the biggest advocate, I think. In my thesis, I used one of these 90-foot antennas with a 960 megahertz receiver to map the Milky Way, the part of the Milky Way we could see from the Owens Valley. I did that by pointing the antenna to the west of the Milky Way and letting the Earth's rotation scan the beam of the antenna across the Milky Way. So the chart recorder you'll see no computers in any of this. The chart recorder would go along as we went into the Milky Way. The power would go up, and then it would go back down. And I only had a certain amount of time, so I would quit and go do the next scan. And later, I would put a meter stick across the bottom and measure up from there. Well, I knew we were inside the galaxy, and I could also see that there was still a certain amount of tapering off at the edge of my map. So I knew it wasn't right, but the Milky Way is very thin compared to its diameter. So I got a pretty good measurement of the Milky Way. After finishing my PhD and finishing up some things I'd started at Caltech in a one-year postdoc, I took a job at Bell Labs Crawford Hill. This is a picture of Crawford Hill shortly after it was first occupied. Those of you who were there will recognize that the trees have grown up an awful lot since then. At that time, the 20-foot horn reflector could see from horizon to horizon. When the satellite came up, they wanted to be able to pick it up and track it all the way across the sky. About the time I was offered a job, Comcast had been created, and so AT&T was no longer really allowed to do intercontinental communication by satellite, but they hadn't really lost interest in satellites. The year before, or I guess a little more than a year before I came, Arnold Penzias was hired. He had done a radio astronomy thesis at Columbia with Charlie Towns. He looked for hydrogen in clusters of galaxies. He built a maser. He did a lot of hardware work for that thesis. He complained a lot about how much he had to do. So why did Bell Labs hire 2 radio astronomers? I think the reason they told the upper management was that we would know about antennas and transmission through the atmosphere and a lot of the things that were needed for satellite communications. But I think there's more to it than that. Art Crawford, who built the 20-foot horn reflector, and Rudy Kaufner, who had overseen the whole ECHO and then Telstar projects, were very proud about what they had done. They knew they had made a unique instrument which could have use for radio astronomy. There also was a leftover feeling of guilt to some extent over not having followed up Karl Jansky's discovery. It had been in the Depression. Much of that time they were working on short hours, and it seemed important to do Bell system business rather than run off into astronomy. Anyway, the attraction to Arno and me was the research atmosphere, generous support, and the opportunity to use a unique instrument, the very low noise traveling wave maser and the small but unique antenna. Both Arno and I had used larger antennas in our thesis. Well, we put together a set of plans, and some of the things we wanted to do was measure the absolute strength of Cas A, and a few other radio sources, which could be useful for both radio astronomy, since astronomers very seldom understand the real sensitivity of their instrument, and could be useful for satellite communications, because if you buy an Earth station, you can look at the signal-noise ratio on Cas A and know whether the gain and noise figure together were as good as you were supposed to have. We would then look for a halo of radiation around the galaxy, Milky Way, at 1.4 gigahertz. In other words, sort of fix up my thesis. And then after having made the 1.4 gigahertz receiver, we'd do a much better search for atomic hydrogen and clusters of galaxy and fix up Arno's thesis. I think maybe young researchers don't always have better ideas than doing more of what they were doing. But we started with the existing 4 gigahertz system, which could do two things. It could do the useful Cas A measurement, and it could do a control measurement for the halo. We knew from extrapolation that the 0 point of galactic radiation had to be too small to really measure at 4 gigahertz. So we could find out that we could actually measure 0. So Arno made a helium-cooled reference load. Here's the absorber in the bottom, a long waveguide going into the helium. It was thin some, but these baffles did a heat exchange between the helium gas boiling off and the heat trying to come down the waveguide. And even though he primarily worked on making it a good microwave device, its helium would actually last longer than we would. We put 25 liters of helium in it, and we could observe longer than we wanted to observe. I put together a switch for comparing the reference load to the antenna, and maybe as time's going by, I should skip over its operation. Here's a picture of it, and the antenna comes in here with a rotary joint. This is a polarization coupler that couples in one polarization the signal from the reference load down here. There's an attenuator in here which can add a small amount of noise. This is a half-wave plate which can rotate. There's another polarization coupler. So in this waveguide, we have the antenna signal in one polarization and the reference signal in the other. By rotating the half-wave plate and picking off one polarization, sending it over to the maser, we can switch between the two with very low noise, and we were able to measure this switch so that we understood its symmetry, could make a good comparison. Well, meanwhile, Dave Hogg and I had rented a helicopter for a day and flown a 4 gigahertz source on it to measure the gain of the 20-foot Horn reflector. If you look, this obviously is an ad hoc thing. And at this, I think maybe they were able to pull up one of these ropes. Otherwise, I don't understand why they didn't destroy the horn when it landed. But up here on the side of the horn reflector is the mate to this horn. And these two had been carefully measured in the lab. And we understood the gain of this one. And there's a waveguide going back down to the receiver so we could switch between. There's a television camera there. So when we had the poor helicopter driver had to try to stay as close to a fixed position as possible. And then we would point and try to track him. When we had everything lined up, we would switch between the horn reflector and the reference horn, and we made relative measurements. And actually, I think did a pretty good job of determining the gain of the 20-foot horn. So a little later, somewhat more than 51 years ago, Arno and I got our radiometer together, and this is a copy of our first measurement. And let's see, here is the antenna. I guess here is the antenna looking at 90 degrees elevation. Here is looking at the co-load. with 0.04 dB added, so a little bit of noise added. You can see that the antenna, the noise from the antenna is definitely more than the cold load. And by all rights, it should have been less. We expected a couple of degrees from the atmosphere. We could measure that, maybe a degree from the walls. And instead of 3-something degrees, we had about twice that much. However, we didn't want to disturb things for a while because we had the careful measurement of the gain. So we spent about 9 months improving our receiver, checking everything we could. We had several different ways of calibrating it. We wanted to get consistent results. And eventually we accurately measured the strength of Cas A and several other radio sources. During this time, the excess noise of 3.5K remained the same. We found no fault in our equipment, nor did we find anything in the environment. So at the end of that period, we got up and cleaned out the horn reflector. You can see the aluminum tape we put on the joints. We thought possibly 2 pieces of aluminum riveted to a rib might not be a perfect conductor, but the tape didn't make any difference. Removing the pigeons and the droppings didn't make much difference. So we tried to think of everything we could, and essentially we were ruled out of everything we could think of. So we were really sort of desperate in trying to understand this. We needed to publish the paper about Cas A, but we weren't sure what we were going to say about this. Then one spring day in 1965, Arno called Bernie Burke. And at the end of their conversation, the original subject, neither of them remembers. At the end of the conversation, Bernie said, "What's going on with your crazy experiment?" Sometime in the previous year, they'd been on a plane to Montreal for some meeting together, and Bernie was pumping Arno about what we were going to do at Bell Labs. I think there was an undercurrent of why aren't you at a researching university? But anyway, Arno outlined the things I told you about, and Bernie's reaction was, "There's no halo around the galaxy, you're wasting your time." Well, in a similar period, John Bolton, my professor at Caltech, came for a visit, and he pointed out looking for the zero level was the most important thing we were planning to do. So we got opposite advice on those things. So anyway, Arno laid it on Bernie, and Bernie said, "Well, you ought to call Bob Dickey at Princeton." Well, the background to this is that the Princeton, what's now called the Princeton Gravity Group, had been thinking about Big Bang. Bob Dickey, of course, was an excellent physicist, did microwave work during the Second World War and wrote one of the Rad Lab books. And afterward started thinking about gravity, and as part of his gravity thoughts, he thought about a Big Bang cosmology, and he was thinking in terms of an oscillating universe, so that at the end of every cycle, all of the heavy elements would be destroyed and it would start over again with fresh entropy. I don't know whether that actually works or not. But anyway, he got 2 postdocs, 2 very good postdocs. Dave Wilkinson, he was thinking about the Big Bang and thought that it would start off very hot, but that as it expanded, the radiation would cool. And being a microwave guy, he realized it would be microwave radiation now. So he got Dave Wilkinson to build a receiver to look for that, and Jim Peebles to make a better calculation of what one might expect. Jim finished up first because it's easy. From my point of view, it's easier to make a calculation than a receiver. And he got an invitation to give a talk at Johns Hopkins, and postdocs don't turn down such invitations. And so we went to Bob Dickey and Dave and said, "Is it all right if I talk about my calculations?" They said, "Sure, we're so far ahead, no one can catch up." So he went off and gave the talk. A fellow named Ken Turner listened to the talk. He was a good friend of Bernie's, went back and told Bernie about it. And the next day, Arno called Bernie. So Arno said, talk to Bob Dickey. So Arno called up Bob Dickey, and Dave Wilkinson tells the story that they were having a bag lunch in Bob's office. The phone rang, picked up the phone, and they heard things like atmospheric radiation, antenna temperature, sky brightness, all the things they were worried about. At the end of the conversation, Dickey put down the phone and said, boys, we've been scooped. So we invited them over. They came over and saw what we had. I think Bell Labs had such a good reputation. They believed us from the beginning. But anyway, they then told us about the cosmology, and I think we were probably more skeptical of the cosmology than they were of our measurement. We were happy to have some sort of an explanation. So we wrote two separate papers. We wrote a little paper, a page and a half long, describing our measurement, referencing the measurement of Cas A, which described the instrument. And they wrote a several-page paper describing Big Bang cosmology and microwave background radiation. We made one final check with a Hewlett-Packard signal generator in one of those horns, taking it around the top of the hill to make sure the horn reflector wasn't picking up junk from the ground that we didn't expect. Then on May 20th, two things happened. One is in the afternoon, Walter Sullivan, who was sort of the chief science reporter of the New York Times at the time, called. We were up in the antenna. Arno talked to him. He asked a few questions about what we were doing. The next thing that happened is that evening, my father came for a visit from Texas. He had business in the central New Jersey the next day. He stayed with us. And the next morning, he got up bright and early. I guess I usually got to work at 9 o'clock. We were lucky. And so Betsy and I were a little slower getting up. So he got up, showered, got dressed, and waiting for us, he walked down to the local pharmacy about a quarter of a mile away, bought a New York Times, and he brought it back. There on the front page of the New York Times was our antenna with a long story about cosmology. And at that point, I started to take cosmology a little more seriously. So, of course, many things have happened again since then, and most of you know much of the story. The cosmic background radiation, of course, is our earliest picture of our universe, and there's a remarkable fit between lambda CDM cosmology started by inflation and what's measured with the microwave background. And in fact, a lot of this is duplicated with optical measurements, things like the Sloan Digital Sky Survey. And cosmology looks wonderful these days, except for the fact that we don't know what 96% of the universe is. Anyway, I'm going to switch subjects now and go back to the 30s. In 1932, George Southworth at Bell Labs demonstrated, I believe for the first time, propagation of radio waves through a waveguide. The next year, Mead and Shelkonoff was a very good mathematician, calculated the loss in various modes in the circular waveguide. These are drawings of the electric and magnetic field in the waveguide, and discovered that this TE01 mode, in which the electric field stays away from the wall, would have very low loss. And Southworth moved to Holmdel. He and Russell and Holmdel started investigating millimeter wave detectors using a spark sort of source. Anyway, they started working on waveguide. Here is Southworth next to a long waveguide in Holmdel. The idea of low loss transmission by millimeter waves in an overmoded circular waveguide remained as a driving force at Holmdel over many years. And as the technology developed, the interest increased. When I joined Bell Labs in '63, there was a group there intensively working on a millimeter waveguide system. It used 2-inch diameter waveguide. I won't go into any of the details, but it could operate between 38 and 120 gigahertz in the TE01 mode. And they could foresee using this to make transcontinental communication. By 1975, such a system had been developed, and they knew they could do it, but it wasn't yet needed. Picture phone had failed. I was going to provide all the extra bits that were needed to be transmitted, but people really weren't very interested in picture phone, at least at the price. The Crawford Hill group, meanwhile, had started working on optical fibers. It pretty soon became clear that optical fibers were a much better idea than millimeter waveguide. In 1966, after some of the excitement about discovering the cosmic microwave background sort of tailed down, and we submitted a purchase order for $1,000 for a Hewlett-Packard part. And our director called us in and said, well, the understanding was that you two guys were going to each work half time on radio astronomy and half time on projects useful to the Bell system. And so far, it's pretty much been radio astronomy. So why don't you find some useful thing to do also? So we both took on communications-related projects. One of the things I did with the Sun Tracker, which Roy Tillotson was still interested in satellite communications. This thing worked at 19 and 28 gigahertz to explore higher frequency bands to see how bad the weather would be for communicating with the satellite. Meanwhile, Arno did another thing I won't describe, but he'd also been working some observing at NRAO and became aware of the 36-foot antenna which they had built for millimeter wave astronomy using Frank Lowe's bolometers. And Frank Lowe at the time didn't know how to couple his bolometers to a short focal length telescope. So if you look at that antenna, you can see that the feed leg is very, very long compared to an ordinary antenna. So it had an F/D of 0.8, as I remember, much longer than most radio telescopes. However, Frank went on to other places, and NRAO had no decent receivers for this antenna. However, down the hall from us, Charlie Burris was in the millimeter waveguide group. He was making small area Schottky barrier diodes using some special photolithography tricks to make 2-micron diameter diodes, which worked in fact very well at millimeter wavelengths. And so in 1968, Charlie made us an 80 to 90 gigahertz receiver using his diodes, using wafers, and using a system of mounting and a waveguide where you could change the diode easily, developed by Sharpless. We took it to Kitt Peak, put it on the telescope to do some source measurements with Ken Kellerman, but the telescope really wasn't ready for prime time. They didn't understand the pointing. There were a lot of other problems, and very little science came out of that effort. We did, however, show that it would be difficult for a set of discrete sources to make up the cosmic microwave background, because this antenna had a nice fine beam. And we took one region and scanned it over and over again and didn't see any lumps. So then we left that receiver at NRAO. Charlie provided NRAO with some diodes in the future. But then in 1970, when the 36-foot was ready for real work, Arno invited Keith Jeffords to join us for a millimeter wave spectroscopy effort. Arno had been a Townes student. He was aware of Townes' list of potential molecules in astronomy. And we decided that if we moved to the next smaller waveguide size, there were a number of interesting molecules we should be able to measure. If I were to sort of following Karl Jansky at the time, the interstellar medium had only a few phases that people were aware of. The synchrotron emission, which had been in my thesis, H2 regions, ionized hydrogen that's just hot and thermally radiates, atomic hydrogen that had been discovered a long time before here, and dust. I think that the idea of molecular regions was not really in the general consciousness. However, the year before, Phil Solomon had published a paper showing that in regions denser than about 100 particles per cc, that molecular hydrogen would form on grains, that would be self-shielding, and it would be quite stable. So there ought to be molecular regions. There weren't very many known molecules. The second bullet item has Towns's list. The first three had been measured. None of these molecules really pointed to extensive molecular clouds, but we thought that looking at the rotational spectrum of CO, which is quite stable compared to the other molecules, might be a much better thing than some of the peculiar spectral arrangements for looking at those molecules. So Charlie Burris built us an RG8 receiver, receiver and RG8 waveguide or a mixer, rated from 90 to 140 gigahertz. Sandy Weinreb at NRAO agreed to provide a lot of the auxiliary equipment we needed. Arno and I built a receiver around Charlie's mixer. Sandy sent the front end box and the control rack for it to Bell Labs. And Keith Jeffords and I spent about 2 weeks frantically trying to get it all interfaced. And we almost finished the job, and we had to ship it to Kid Peak. So then Sandy, Keith, and I went to the 36-foot to get it all going. And we discovered that all sorts of parts had ways of failing. And one of the more serious ones was the klystrons, which were very expensive. $5,000 klystron you can buy a very nice car for. And they would spark. If you caught it quickly, you could turn the power off and then very slowly turn the power back up, and it might recover. It might also take out the transistors in Sandy's phase lock loop. And you'd have to work on that. Anyway, after 3 days of a lot of frustration, Sandy had to go back for something at Charlottesville and left. He was very discouraged. I don't think he told us at the time, but he's told me later. He just didn't think this was ever going to work. So anyway, later that day, after Sandy had left, Keith and I miraculously got it all going. We told Sandy he was not part of the problem. Remarkably, we took the receiver box, this sort of size, and put it up at the focus of the 36-foot on long cables that they had, and remarkably, it continued to work. So I asked the telescope operator, I looked on our list of sources, picked out the Orion B and KL region, and asked the operator to point the antenna there. And the receiver had a 40-channel back end. Each channel had a lock-in amplifier and an integrator. And these were analog components. Each had its own offset and gain. And there was no real attempt to make them all equal. And the integrator had 2 modes. In one, it would just straight integrate. In the other, it was a 2-second time constant. So I had it set as a 2-second time constant. There was a multiplexer which would step through these things and display the all the 40 dots on the face of this oscilloscope. Now, unfortunately, my Kodachrome picture didn't pick up any of the dots. But so I was standing there looking at the dots on the face of the oscilloscope, and this was just sort of a cloud of dots moving around. And suddenly, the ones in the center went up. And I asked the operator, "Did you get to the source?" "Yes." "Well, please move off." The dots moved back down. So, unlike the labored discovery of the cosmic microwave background, this was instantaneous satisfaction. It took only a few seconds to discover CO. Unfortunately, at that time, the integrator could, while it could integrate for many minutes, at the end of the integration period, it dumped all its values. The same multiplexer dumped the values to magnetic tape and erased the integrator. And that was the last you saw of it until you went downtown. Well, at that point, we didn't even have a program to run downtown to look at this stuff. So we did a bunch of measurements. It was a rather frustrating way to observe. But anyway, I observed 2 second, well, let me say first, Arno only showed up the next day. While Keith and I were working at Crawford Hill putting things together, Keith quipped that Arno had the 2 best technicians at Bell Labs working for him. Well, Arno missed out on the discovery. He showed up the next day. Anyway, I patched together 2 spectra, 2 sort of narrow band spectra to make a full spectrum of Orion A, which is what we published in our paper. And one of the disappointments of my career is that we didn't properly pay attention to these wings on the line. It was only about 7 years later that it was realized that those wings are a result of a bipolar outflow from that region. And we should certainly have known to not ignore something like that in our receiver. There had to be an astrophysical effect going along with those wings. Well, here is Arno, Keith, and me at the 36-foot antenna. There was one computer there. It stood, I don't know, almost 2 meters high. It was 3 racks wide. It was a DDP-116, a very early mini computer. And the only thing it did was convert coordinates and drive the antenna. It was an alt-azimuth mount antenna. Didn't help at all with the data. So over the next summer, Keith had ordered a Nova computer, 16-bit mini computer, and over the summer, I wrote a program and he made some hardware so that when we went back in the fall, we could actually capture the data ourselves, normalize things, and really look at spectrum. But a remarkable thing about our first observation is that it happened that we looked at the brightest CO source in the sky first. Of course, CO is probably the brightest molecule in the sky. And after exploring, discovering that this was an extended source and that it was rather broadband, when Orion finally set, we went to bed and slept for a while after not having very much sleep. The next day we got up and the galactic plane was up, and we discovered many more H2 regions had CO sources associated. And millimeter waves allowed rotational transitions of many species to be measured. And we had many times going to Kitt Peak with new ideas of what to look for and a lot of success doing it. It was really an amazing time and a lot of fun. We had many joint projects with Pat Thaddeus and Phil Solomon and their students. We worked hard. There were a lot of new molecules, a lot of instant gratification. At one point, I remember a day, 24 hours went by, and we had something we were looking for, and we never did find it. I remember feeling sort of depressed about it. Seems kind of silly in retrospect. During that period, we worked with Pat and the Harvard College Observatory people and set up the millimeter wave observatory at McDonald Observatory in West Texas. Did some work there as well as at Kitt Peak. We also planned a 7-meter antenna at Labs. This, as you can probably tell, is an offset antenna, but not offset by 90 degrees, but only enough to keep the subreflector out of the main beam so that it had a clean main beam. This antenna had two purposes. Roy Tillotson, the director, wanted us to do useful things. We wanted to make better measurements of satellite communications, and had arranged for a beacon on the Comstar satellite. So we could, during bad weather, we would point this at the Comstar beacon. They had two receivers, one on axis and one slightly off axis, to see if scattering and rain and so forth would scatter the signal into the other receiver. Anyway, they operated for several years. Every time the weather was bad, they got a lot of data about satellite communications. When the weather was good, we would change the computer program and do millimeter astronomy. Once we had a solid state local oscillator, we used to I would go up sometimes in the morning, set up an observing program, and it would run till the evening, and someone would set it up in the evening to run overnight. The thing ran unattended a lot. Well, Tony Stark did a lot of galactic work. John Valley did extensive mapping of molecular clouds. Bill Langer and I looked at a lot of details of cold clouds. And we did a lot of astronomy during the 80s with the 7-meter. But to sum up, I would say that those two guys in 1965 didn't have any idea what a big thing the cosmic background radiation was, what was going to be. Looking back on this, I feel very lucky. I had a job at Bell Labs and was supported to apply technologies Bell Labs developed to communications, for communications to astrophysics. There were many experts there who had written the book about one thing or another. They were happy to help. The reward system at Bell Labs rewarded people for cross-disciplinary work, which I think was a very, very important aspect of Bell Labs. I started my career when radio astronomy and cosmology were relatively young science, but poised to blossom as technology developed. When I entered the workforce, the nation, perhaps shocked by Sputnik and remembering the contributions of science to World War II, understood the value of science and for its future was willing to spend the money to be the world leader in science and technology. As I've said, the CO provided instant gratification, the CMB didn't. The importance of the CMB only became clear over the following years as theory and technology developed and the receivers developed simultaneously, each driving the other. It is, however, very satisfying to look back and see that we did the right thing and how much has been derived from the cosmic background radiation. It's been a wonderful ride. Thank you. Any questions? If anyone has any? Yes, Charlie.
And between Jansky and the post-war developments you talked about so much, Karl Reaver was doing some interesting things in
Yes.
Illinois. Did that have any impact or influence on the radio engineers at Bell Labs?
I think they were aware of it, but they never talked to me much about Reaver's work. They did talk a good bit about Jansky. I guess I forgot to say, Art Crawford was our first department head. And so we heard a good bit about that, but I'm sure they were aware of it, and that may have gone into why they were interested in supporting some more radio astronomy. But of course, there had been radio astronomy after the Second World War then, and discrete sources had been discovered. Hydrogen line was known. The Australian group was active. The Cambridge group was active. So I'm not sure Reber's work had much influence on it. I think that's
Given the abundance of innovation develops and the atmosphere that was created, that was in the business world.
Mhm.
Are you somewhat disappointed as to the atmosphere that is now in academic research that is not as risk-taking as maybe other?
Yes, I think the management of Bell Labs in some remarkable way was truly excellent. And the support, well, the support was done effectively by a tax on telephone bills. Something like 1% of the nation's of the Bell System's telephone bills anyway, was used to support research at Bell Labs. And I think it was an important thing at the time because not many other people were working on equipment that could improve the telephone system. And I think the Bell System in the country got a lot out of it. But you know, being here in a government lab, I see a lot of rules that apply that did not apply at Bell Labs. And it was a lot easier to do what you wanted to do at Bell Labs. We had a remarkable shop. I took out a picture of me standing in the shop. It was a huge shop. Guys who knew how to make waveguide anything. You go and you wave your hands. They would complain about the cartoons we drew, but they would give us exactly what we wanted. And these days, certainly in business, the Wall Street is forced a very short time window. NSF wants to know what you're going to do. I guess some people may cheat and say what I've already done that they're going to do, so they know they'll do it. But there's not the open-endedness that existed then. It's really disappointing. I'm a little worried for the future of the country.
I can take one more. Two more. Yeah.
Well, during your time at Bell Labs, did you get to meet some of the transistor guys, Bill Shockley or Claude Shannon? Or
I didn't actually. We were about an hour away from Murray Hill,
okay.
and didn't get to Murray Hill very often. It's surprising here how much the difference between 60 and 160 makes in the And at Crawford Hill, those of you who've been there realize it's a fairly small building with 150 people maybe. And I got to know where all of the Hewlett-Packard test equipment that I might need was stored in labs and cupboards up and down the hall. And I knew people who were experts about everything, and it was remarkable. At Holmdel, at Murray Hill, it was again a building with a very long hall. And people in retrospect said that that was a marvelous thing because going to lunch would pass all sorts of people. The Holmdel building had a bunch of short halls and people missed that. There really is something about designing the building right to get people to interact in an informal way. It's important.
All right, let's close off with one more. Just one more question.
Phil,
We came with the 7 meters also.
it's sitting there rotting, quite literally. The cabin and the control building were built by our carpenters in wood. A Princeton group, Dave Wilkinson's, Suzanne's group did a map of the North Polar region with it. And when they left, the Mylar window broke and some coons got inside. And It's a mess in there now. It needs to get up there and hose the whole thing out, but in fact, I don't think the thing has much future, and it probably is going to be taken apart. Various people wanted to move it. I think Suzanne Staggs wanted to move it to Chile, but I don't think that'll ever happen now. So I think it's gone. Although you can still see it. Thank you.
Okay, so thanks very much.